Alright, I'm going to do my best to explain how traffic engineering works and how I have it working. It is not the way that I was shown last night, but it seems to be working. So I've changed my topology up a little bit. I took a router out of here in the middle to shorten the amount of hops, just to further make the system want to route this way. So what we're going to do now is we're going to open up the label edge router 1 and the label edge router 2 because that are my MPLS endpoints. So we're in the LAR here. And we have a traffic engineering interface. It is called TE1. We have a tunnel path. One is dynamic and one is tunnel path 1 just because I didn't have anything else to name it. And I've told it the hops or the direction that I really wanted it to go loosely. So what that means is dot 10 is here and 18 is here. So it's going to go this path. If I had LSR2 connected to LSR5 and back to 4, it could go all the way down this way or it could go this way. Long as it ends up here, the path is loose. You can set it to strict. It's just that in my demonstration here, it is not needed. And then dynamic uses CSPF, which is we had to enable in OSPF. I did not have this set the other night when I set it up. It's on the MPLS tab of OSPF. This is the normal stuff that we fill out. There's an MPLS tag, so you tell it the backbone or the area. Ours is backbone. Basically, area is 0. And then the router ID is the loopback. So what that does is it takes some extra information about the traffic engineering interface. So we said this traffic engineering interface 1500 bytes. The bandwidth is 1K because we're just toying here. We'll put real bandwidth values in when we start to use it. And then Ether 2 and Ether 3 are the interfaces we want traffic engineering to take a path on. And you can see because the tunnel is active, it is telling me that my remaining bandwidth on Ether 2 is 99 kilobits per second because I have the traffic engineering interface and it is running currently over this way. And the way that you can tell that is we click here and you click status and it tells it our route. So it goes 6, 10, 18, which is the loose path, and the recorded route is, all the interfaces it hits, which is 9, 13, 17, 21, 22, all the way over to the other LER, and I have a reserved bandwidth of 100 bits per second. So this is how you actually keep up with how much traffic you have remaining, so you don't oversell a circuit. And so, all right, that handles how traffic engineering happens. This does not do anything without VPLS. So I think VPLS is a layer 2 bridge. It's a 1500 byte MTU. So the total packet size is 1508, and MPLS will just switch it on down through the network. Most devices are fine. I forgot the official RFC number, but Mikrotiks will switch 1508 byte packets right out of the box. So what we're doing here is I have a VPLS that ties LER1 and LER2 together. When you have a traffic engineering interface, the VPLS automatically follows the traffic engineering interface. So if you do not have a traffic engineering interface, the VPLS will follow the open shortest path, just like OSPF would tell it, or default MPLS would tell it to take the shortest path. When you turn on traffic engineering, the VPLS follows the traffic engineering path. So the VPLS is here. Let's make a bridge. We're gonna call this cust2 because I think that's what that's called. Let's put the VPLS and customer 2. Customer 2 interfaces with the LER on ether 3 of the LER. So I'm sure we just broke something seriously. I'm going to take its gateway address that's on the LER for customer 2. We're going to turn it off. It's now stopped injecting that route to the network that is on that interface. So customer 2 should be off the map. It is down. So let's go back over to the LER of 1 and let's put that address on it. Let's see what happens. So I put the address on the VPLS because the customer router is expecting a DHCP address. I'll just put one on the VPLS real quick. And I don't know if I should static this or put it into routing because I do not have redistribute static route. So if I put static route and say that that's up to, I don't know. We'll see what happens. Sorry for the experimental video. Oh, it's already in there. Must have tried that one other time, something along these lines. Alright, so now that's happening. Customer 2 is on the VPLS. It definitely gets timeout. It don't even find its gateway. LER, so I got customer. Oh, look at this. I put ether 3 in the loop back. Rookie mistake. How about that? Now the customer's on bridge to the VPLS. The VPLS is bridged to LER 1. And look at that. I can get out. There's the address of the LER. There's the address of one of my physical routers. There's the next physical router in line and the public network. So we know that the traffic engineering is enabled. The VPLS is taking the path on the LER, or the VPLS is taking the path of the traffic engineering. Sorry guys. Starting to lose myself. Alright, so let's see if Winbox will trace route, because it would trace route before from the console, but wouldn't technically get out. And it is, and it shows it's working. Alright, so we have a connection there, it's working. I'm going to close Winbox. We don't need it running, because now that that's working, I have an idea of how we'll do this. We are pretty much going to have to do like I was explained, having the gateway at the other end of the VPLS. It'll be a bigger network, let's say a /27 or 6 for however how many customers are going to be at the other end of that network. will assign their addresses by PPOE or radius with DHCP or something. So that's working. We're not having any funky routes. So what we are going to do is we're going to leave customer 2 up. It's got a trace route running. What I'm going to do is turn off traffic engineering on LER2. And we're going to see what happens to the VPLS, because it says it's on transport tail 1. So let's just turn that off. The VPLS went down. It came back up. Transport next hop of .26. I'm going to restart our trace route. We can still get out to the customer. Still looks like, you know, they're 2 hops from their gateway. Let's send a ping out. We are getting some pings. That's good. So the network is up. And the way that would work is, because traffic engineering can go one way without the other, you don't have to have it explicitly turned on. This one is going down 32.26. 32.26 is on LER5, and I will show you that. We'll open up LER5. See, here's the IP address 32.26. Well, yeah, you can't see the real trace route because it's going over the VPLS. But I can tell you that traffic going out from the customer is going this way and out to the internet. I wish it would stop highlighting. And traffic coming in is actually still going over the VPLS this way. Because if we go to LER1, get rid of this, its VPLS should say status transport traffic engineering 1, transport next hop 32.6. 32.6 is on LSR1, Ether 1 should be. Yep, 32.6 is on Ether 1 of this router, and it is going this way in. So now we have split route, because I'm not explicitly telling the traffic to go out on the traffic engineering. So I hope that I'm starting to make sense. Sorry for the goof up there in the middle. I was just trying something new that I briefly tried before I turned the video on, and it seemed to have worked, but definitely really caused some routing loops, which is good that we're practicing in GNS3 and not out to the customer. So I hope that this is showing you how traffic engineering is working. We can also turn it off here. You notice the transport next hop is .37, and I told you earlier .37 is on LSR6. Just to show you LSR6, here's .37 is on Ether 2. So LSR6, Ether 2 is connected to Ether 3 of LER1. So that's the transport path now, because I disabled the traffic engineering, forcing it to go this way on the inbound. It was already disabled for the outbound. So now the traffic is going on the VPLS the way that it normally would. The customer still does not notice any difference, because the trace route, I shouldn't do trace routes to Google, I know the internet it's working, but to them it's one hop to their gateway, and boom, technically they could hit the public internet in less than 4 hops. It would show, because you're going to have a core. This is going to be your core router here where all your VPLS endpoints hit. You're probably going to have your BGP router somewhere in here, somewhere between these 2 routers, hanging on a switch-ish in there. There's going to be your radius server, whatever, PPOE, if you're doing that, whatever you're using to authenticate your clients. We could still static address them. There's no reason that you can't stack all, /30s for each customer, or whatever we're doing, or one big network. We don't have to turn on DHCP. We can still just put the gateway there and still have to statically assign each customer, even though we'd like to get away from that, do something more automatic, even if it's through hotspot. At that point we can hotspot and use hotspot accounts, and so if they have a hotspot account, they automatically get a public address. There's kind of open to however you want to do it, but that is my traffic engineering the broken way and the working way. So here's LER 1. I'm going to enable traffic engineering. You notice the transport next hop just changed. It's now going the other direction. The VPLS briefly reset, but just a minor blip. This one flip. Now the transport next hop is going up to LSR4. I have not shown LSR4 in this demonstration, so let's close LSR1. Sorry guys, is that alright? Close Winbox. So I'm using the .18 address to get to LSR4, but here's the .21. Here's the address that the transport next hop is going out. So I hope that this is showing how traffic engineering is working, and what it does do, what it does not do. We can also do bandwidth. We can impose bandwidth restrictions. Say here on LER1 for the VPLS, we can say we can do a queue, just make a simple queue, blah blah blah. You can do it by IP addresses. We can do it by targets. You can do like the standard things that you can do. We can set up maximum amounts, so the whole /26 has 50 megabits of traffic. It'll automatically equalize the traffic between every IP address and connection. So we try to everybody could use as much as possible, and then as more people come online, the router will try to equalize the bandwidth between every connection until it's split equally between every customer on the other end of that VPLS. This is for like your home user style. If this was an enterprise customer, which I plan to do over here, we would just do managed MPLS all the way down to the customer's router. We would not inject the customer subnet, but we could manage this. So technically, if this customer was hanging off over here, which is where I'm probably going to put it for the next demonstration, we could run the VPLS directly on it with traffic engineering, and it would, it could take a different path than this customer here, because all the customers that are bound to this router with traffic engineering, they're all the same. So we can stick as many VPLSs we want to on here, but they will follow the same traffic engineering path is what I've set up for that router. You cannot specify which VPLS runs on what traffic engineering at the moment. I don't know if you can do that in the upcoming router OS that is like a unicorn that may or may not ever come out, but they're saying like summer of 2016. I really don't even think it's built into the protocol, but it would be really nice if you could specify which traffic engineering interface a VPLS was primary on, and then it could dynamically move over, sort of the same way the tunnel paths work. You could specify different traffic engineering interfaces for the VPLS. So you could say like I want a primary to run on traffic engineering 1, and if traffic engineering 1 gets disabled, this VPLS automatically moves over to traffic engineering 2, or however we name these. That way, these tunnel paths, we could build different routes and then shift things differently. This will be real handy to send voice over IP down the shortest path and send regular traffic to the longest path. But to do that, we're going to do some angle rules and some other stuff up on the customer's interface. I think we can do that. So if we have a customer that needs 2 sites on the same subnet, we can just do a VPLS directly between the two. To create a VPLS is pretty simple. Remote peer, VPLS ID, the increment, same way like you keep track of your numbers for EOIP. Imagine you can turn on the VPLS ID, and it is on. It's just probably way at the end. There it is. So way down where you would never really see it. I'd like to move these. A lot of times I turn off all these firewall packets per second, just so that way I can get some better information down here. And for this, there it goes. Having some issues dragging. That would be way many. That field should be big enough for lots of bandwidth. So like these here are not even needed, because it's not a firewall, that's a firewall packet. So you could turn those off, and that would get this in here. And then you see your VPLS ID, your next one's got to be up a little bit. And so you could, that's 0:0. I imagine you could say like customer A is 0, but their sites increment in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think. Or it may be that 0 is always 0, and it doesn't matter what this number is, it would bind it together. I got to read the manual here for what the ID means, but I know if it doesn't match, the tunnel usually does not come up. But I guess as a quick demonstration, we can make this 0:1. If the tunnel goes down, it is down, so it's got to be the same on both ends. See, our tunnel is down. And because that tunnel is down, I bet you this customer has no internet, because their gateway is at the other end of the tunnel. So let's turn it back on. It registered, and it's back. It's pretty instant in the registration. You can see we've got a little bit of traffic. So this is MPLS traffic engineering do's and don'ts. More along the lines of I was trying to figure it out while we were doing the video. So thanks for watching.